Hello and welcome back to my channel guys. Today we are going to see how to design a column. So here we are doing a column design for steel structure by Euler's critical load formula. In this chapter we will learn how to calculate effective length of the column LE, buckling load on a column LB and bending stress of the column. So let's start guys. Now in this figure we have considered two columns which is connected with some beam. In these two columns, the columns are fixed at the bottom and they are hinged at the top. 600 kg load is applied on the column each and there will be some moments coming in the column due to the load applied on the beam which is 1.2 tons. So this column having a load from two directions. One is from top which is a product load and another which is creating a twisting effect in the column or buckling effect in the column which is F. So now check for buckling. The column condition is one end fixed and one end is hinged. Here we will find an equivalent length of the column. So equivalent length of the column which has a one end fixed and another is a hinge is 0.699 into L. L is nothing but the length of a column. So the value comes 3320.2 millimeter is the effective length. Now we will try to understand where this equivalent length or effective length formula come from. In the column there are four conditions usually comes, which are like both end are hinged in the column or both end are fixed in the column. Third is a one end fixed and other end is hinged. And the last one is one end is fixed and other end is free. So these are the four conditions of the column usually we find. In this one we will see how to calculate a buckling load for each column and how to find out the effective length of each column. For the buckling load of the column, these are the Euler's formula has been defined, where we can put these values directly from catalog sum and from a figure and we can get a buckling load of the column. But to calculate the effective length of the column, we have a separate four different formulas for each condition. If we consider a first condition where the both ends are hinged in the column, their LE, which is the effective length, is equals to L. The actual formula of effective length is LE equals to KL. K is nothing but a theoretical value, and this theoretical value actually makes a difference. So in both end hinge condition, this K is equals to 1. So you can consider this LE equals to L in the both end hinge condition. Another condition where the both ends are fixed in the column, the value of K is 0.5 into L. The third condition where the one end is fixed and other end is hinged, value of the K is 0.699 into L. In the last condition where one end is fixed, another end is free, there the value of K is 2. So you can learn from this figure, the more the value of K is tends to more deflection in the column. So lesser the value of K actually is better in this scenario. So here we will see that both end fixed column is more stable than the other one. So designer first choice has to be both end fixed column. But if he cannot do this one, he can go for one end fixed and other end hinge condition, which is the second better condition in the column because the value of K is lesser than the other two values in the formula. So lesser the value of K, better for the column buckling. So our condition which is mentioned here is one end is fixed and another end is hinged. And we are taking that 0.699 into L value to find out the effective length here is from this formula. Now once we get the equivalent length of the column, we can check what are the given we have in this problem. So we have considered ISMC 150 channel for this calculation, where the modulus of elasticity of the column is 21 into 10 raised to 3 and moment of inertia of this column, or you can say ISMC 150, is 1576 into 10 raised to 4. If I is not known, then can be calculated by I equals to A into K square minimum. A cross-section area of member, which is A, and list of radius of gyration is K. So from there we can find out a value of I. Now we will see how to calculate buckling load, which is LB. So from this formula we can understand that with the condition of one end fixed and other end hinge, we can get this formula from here. 2.045 pi square EI upon L square is the formula. Actually this must be LE square, because this we are taking is the effective length of the column. So once you put all these values in the formula, the answer comes 60.59 into 10 raised to 3 Newton, which is called a 6059 kg is allowable load on the column, and we are putting barely 600 kgs load on the column. Here this condition actually gives us a chance to reduce the size of the column, so we can reduce the size if needed. So the selected column in this case is safe for buckling. Now we will see how to check a bending stress of the column. Here we have given some considerations, where conveyor speed is 12 meter per minute, weight of the product is 1 ton, and starting and stopping time of the product, or you can say motor, is 3 seconds. Here we have considered some different load for the better calculation purpose. Speed of the conveyor is 12 meter per minute, so S equals to 12 upon 60 seconds, which comes to 0.2 meter per second. So we have just converted from meter per minute to meter per second. Now calculate acceleration. Acceleration is nothing but S upon T. S is speed of the conveyor and T is the time taken by the motor to ramp up the speed. So 0.2 divided by 3, which comes 0.066 meter per second square is the acceleration. We will calculate a force by the formula of mass into acceleration. Mass is nothing but a 1 ton and acceleration is nothing but a 0.066 meter per second square. So F, which is a force, comes to 66 kg meter per second square, which we call as a Newton. So 6.79 kg is a force can be applied. Now we will calculate a moment on the column. So moment on the column can be calculated by the force into distance, which is F into L. F is nothing but 10 kg. We have just rounded up this figure, 10 kg, and 4.750 meters is a length of a column, which is given in a figure. So moment M is equals to 47.5 kg meter. Now we are calculating a bending stress here. So bending stress is nothing but a moment M upon Z is a section modulus. So this value of Z we can get from the catalog of ISMC 150 channel. So M is nothing but 47.5 into 10 raised to 3 and Z is nothing but 106 into 10 raised to 3. So it comes to 0.44 kg per meter square applied on column. So this is nothing but a bending stress applied on the column. Whereas as per the IS standard, 8 to 10 kg per mm square is allowable as per the IS standard on the column. So as per the buckling load, or you can say critical load, the bending stress calculations for selected column is okay. So this way guys, we can calculate a bending stress on the column, then we can calculate how the buckling load coming on the column, then we can check for the effective length of the column. So thank you very much for watching this video guys. Please do like and subscribe to our channel and hit the bell icon button to get our new videos on time.